Hello, everybody, and welcome to the final webinar of our three-part data science series, Models in Production, a look from beginning to end. I'm Julia Sommer, Marketing Manager at Cloudera. Today, we're joined by Sean Anderson and Sean Owen. Before I hand over the reins to presenters, just a few quick housekeeping items. We will have time for Q&A after the webinar, so please type your questions in the chat box. Also, the webinar is being recorded and will be both sent to all registrants and available on the Cloudera website on our resources page along with the presentation deck. Now, without further ado, I'd like to hand it over to the Seans.
Thanks, Julia. And I want to welcome everybody to the third in our series of webinars highlighting a new tool from Cloudera called the Data Science Workbench. So far in the webinar series, we've covered an overview of the new tool and some examples from Matt Brandwein and Tristan Zajanik. In our second webinar, we had a deeper dive into some workloads around machine learning and deep learning using Spark and the Data Science Workbench. So if you haven't viewed those first two webinars, I would encourage you to view them. You can download or you can view them from our resources section. Simply type in Data Science Workbench to that search field. So encourage you to check out the first two in this series and want to welcome you to today's conversation. When we first started this webinar series, our product, the Data Science Workbench, was in private beta, and I'm happy to announce that as of last week, we are now generally available with the Data Science Workbench. So if you like some of the tools used on today's webinar, if you're curious to understand a little more, get a demo, or actually try the technology for yourself, I encourage you to reach out to anybody at Cloudera, your account rep or otherwise, or visit our download section of our website for more information on how you can try out the tool. So for this webinar, we're going to talk about the concept of putting a model in production. And since that concept can take on many different permutations and the surface area of models into production is so broad, I've invited Sean Owen, Director of Data Science at Cloudera, to cover some examples of model serving. Sean works with many of our users to design and begin to implement their data science and machine learning ambitions. And to make things a little more confusing, I am here. I'm an additional Sean Anderson, and I focus on our data science and machine learning products and campaigns here at Cloudera. Julia covered some basic housekeeping items. For one, this webinar will be recorded along with the first two in the series and available to you on demand. And the slides from today's conversation will be posted for future reference. If you have any questions during the conversation, please submit them via the chat window on the bottom left-hand corner. We are going to hope to answer some of those questions time permitting. So in the spirit of time, let's get started with our conversation today. So not to over-rotate on the subject, but we are all well aware that modern data science may consist of multiple stages. And many of the stages that I show here actually even happen after the initial domain research and hypothesis development. While Hadoop brings the promise of unlimited data, not all of it is readily accessible with common data science tools. So we understand that today, using data in data systems like Hadoop often requires some wrangling and data prep to make it analysis ready. To its credit, Hadoop and the Cloudera platform have advanced the practice of delivering data pipelines for analytic environments, which is really helpful when you're designing more self-service environments for data scientists to work more freely on top of. The next stage, and our hypothesis today, is that most of this secondary stage doesn't happen on the cluster today. And this is where the modeling and feature testing and visualization are done. And generally, we think that that is done outside the cluster, either on a laptop or an IDE environment. Many of our users often tell us that they extract data outside of core systems and then instantiate other environments to do the data science work. We'll talk about some of the limitations of this type of strategy a little bit later in the conversation. But we'll just blanketly say today that this is probably not the most ideal scenario for our customer base. And while that's all fine in practice and probably the status quo today, it can precipitate some future refactoring when we try to put models into production in distributed systems like Hadoop and leveraging access engines like Apache Spark. So for many organizations, even the idea of putting a model into production is simply a non-starter for them, based on the way that handoffs happen in between initial ingestion, data prep, data science, and then distributing that out to the masses as a whole. And we'll kind of double-click on that right now. Here at Cloudera, we hear about two common data science modes. The first is around exploratory data analysis. And this is one where the goal is really to help understand the data, analyze it, and then share the results with the others. The outputs of these exercises are often very static, and it might be a dashboard or a PDF or some sort of static asset that I'm handing off at the end of this exercise. And the goal here, specifically for enacting this type of data science work on Hadoop, is really just to point the data scientist at the relevant data and provide it to them in more or less a self-service fashion if possible. Another very popular mode that we're seeing arising, especially for our customers that have very mature data science practices, is this idea of operationalizing or producing data products. And this is where machine learning is embedded to production applications, and the end result here is often something like an online embedded application or an API endpoint. And this operation really brings in more distributed systems knowledge, and oftentimes is more of a parlay in between engineers and data scientists, as they often have kind of conflicting areas of expertise and conflicting motivations here. One example of that is maybe your average data scientist is not really willing to sign up for PagerDuty if the model that they produced goes down in production, nor would they be very effective if they knew that their model went down in general. So our goal here at Cloudera is definitely to try to serve both of those use cases. While we don't believe one is more preferential than the other, many of our organizations, specifically in the Global 8000s, are trying to solve for one or both of these modes. And we definitely see an appetite in our user base to move to more of an operational mindset when looking to deliver analytical projects. But unfortunately today it's challenging for teams to succeed with either use case, let alone both of them. So what does the common data science workflow look like? And we see this in three distinct steps. An initial data ingest or engineering or processing step where we're ingesting data, cleansing data, and preparing data. And then the actual development of the models themselves, where we're exploring data, we're identifying features, we're building models, and we're training and testing those models. And then finally at the end, trying to serve up those models in a capacity that allows us to get more mileage out of the analytical models that were built all over a much wider breadth of data. And when we think about Hadoop as a platform and Cloudera as a platform, I generally like to say that we're very helpful on the left-hand side of this equation. So you don't have to look very far for customers of ours that have gone on record to say that we've decreased their data processing windows by orders of magnitude, whether that's generic ETL processing or building out more robust data pipelines. So today, I believe Cloudera, and specifically with our leadership in technologies like Apache Spark, has a lot of accolades in delivering on the data engineering step. Then once a model is actually developed, all of the features have been built out, all of the testing and training has happened, we actually have some capabilities with data stores like HBase and in the future Kudu to serve up models with very low latency and high throughput. Which leaves us with this middle section where all the visualization and the data wrangling and modeling, testing, and training is happening. And generally, again, our hypothesis is today that this is not done inside the Hadoop cluster. So by pulling this outside of a centralized platform, this presents some problems, namely around things like security. So if I'm extracting data out of core systems and loading them on the laptop, then I have the same security challenges that I did when I was a BI user extracting data into a CSV or an Excel file. It's outside the governed repositories. It's generally considered a kind of gray zone when it comes to data visibility and data governance. And so all of those things that come with extracting the data out of systems are often problematic about this notebook type of scenario. And then generally, improving the experience between these sectors here. So once we've ingested and processed all of this data, how do we make it analytics ready and self-service to the data scientist? And then once the data scientist is developed in their environment of choice, how do we make sure that that translates into production without a whole lot of heavy lifting and refactoring? There's some other limitations as well that we see. The first couple are around access. So many times for the data scientists specifically, they don't often have ready access to secured clusters, namely Hadoop clusters. And so they rely on IT and their engineering counterparts to ensure that they get access to that data, or that data is extracted in whatever cadence is beneficial to the data scientist. However, once they receive that data, still then many of the popular frameworks and libraries can't read Hadoop native data formats out of the box. So some further operations often have to happen there as well. There's an issue with scale. When we're subsampling data out of a core data system and loading on a laptop, then we have to make a lot of inferences about the data that we're working with. And so while today we believe that to be the status quo, just like with doing things like business intelligence, we do believe that access to more data in the model development phase and the model testing phase, we believe will precipitate better analytic end results. And then on top of that, many of the popular frameworks and libraries that are used in these single node environments don't often parallelize across the cluster in as elegant a manner as we would like them to. So some further work through various open source ecosystem projects are happening there, and Sean will talk a little bit more about that in his conversation a little bit later. And then just generally a disconnect with the developer experience. Many popular notebook technologies today don't work well out of the box with Spark. Many of the distributed system notebook technologies look very foreign or different to a Python or R developer. There's also this idea of package deployment and dependency. So if you think about all of the different libraries and all of the different permutations of even, say, one individual Python environment that you would have, you can imagine a scenario where you have 20 data scientists all with differing libraries and different needs. So IT's ability to deliver an environment for each one of those data scientists with all of those permutations baked in, it begins to be very hard to track down. And I think moving forward, a lot of virtualized and agile types of solutions are being developed to attack exactly that management of dependencies. So like I said earlier, we're really here to talk about a new tool being released from Cloudera called the Cloudera Data Science Workbench. The Cloudera Data Science Workbench is a new tool from Cloudera that helps harness the breadth and power of open source data science, all of the tools and libraries and practices that people use today that allow data scientists to bring their favorite tools directly to the data versus extracting that data into a notebook or another platform. The Data Science Workbench is deeply integrated with Hadoop data storage like HDFS and HBase, and connects to access engines like Apache Spark and Impala. It uses the same governance and security that is layered all over the entire system, and so it authenticates via Kerberos and enforces many of the governance and security aspects that are enforced across the Cloudera platform in general. And with the Data Science Workbench, data scientists can use R, Python, or Scala directly from their web browser with no additional desktop footprint. And it allows them to install any library or framework within isolated project environments with direct access to secured clusters and leveraging Spark and Impala. Those data scientists can share insights with their team, and we hope that this will help create more reproducible and collaborative research. And for the data scientists as well, we also give them the ability to automate and monitor data pipelines using a built-in job scheduling feature. For our IT counterparts, we really want to allow them to afford their data science team the freedom to work with technology and data the way that they want to, while still staying compliant with out-of-box support for all of the full platform security, especially Kerberos in the Hadoop ecosystem. And we want to give them these capabilities with the ability to run on-premise and across public clouds, wherever the data that we want to analyze is being managed. So while we're here today to put a lot of focus on the data science workbench, I do want to kind of level set and say that today we believe that data science is a full stack problem. And we believe that having Apache Spark or having the data science workbench is not the one singular tool to deliver on this. So going back to my early diagram about data ingestion and data processing, for that, Cloudera's platform has components like Kafka, Spark Streaming, Apache Spark, access engines like Hive, all aimed at bettering the experience and giving tools for data ingestion and data processing. And now for that middle section, we have the data science workbench that provides the capability to do iterative data science, to test hypothesis, to build out popular Python models based on connectivity with Spark resources and data that lives in HDFS. And then we need to be able to deliver that where auditing and lineage and further data tracking is present across the entire flow of the data coming into the system, the data being analyzed, and the data being delivered as part of a productionalized model. And part of the way that we do that is ensuring that you can deliver that both on-premise as well as in the public cloud. And we also want to ensure that several of our ecosystem partners, people that produce algorithms like H2O and DataRobot, other providers that provide handy tools to connect our ecosystem components and Python ecosystem components with the greater Hadoop ecosystem, including Apache Spark, is absolutely relevant here. So while there are a multitude of vendors that can facilitate one or a couple of these aspects of the data science journey from beginning to end, we believe that Cloudera as a platform, increasingly with the advent of the data science workbench, is now very well capable in delivering on this end-to-end data science promise. And to talk more about the end specifically, I want to pass things off to Sean Owen, who's going to spend a little time talking about the data science workbench, talking about ways that our customers are deploying their analytic projects. And without further ado, Sean, I will shove things over to you.
Great, thanks, Sean. Hello. I am excited about the data science workbench because it does complete the picture on Hadoop. It lets us do the exploratory data science alongside the data engineering and even the model deployment we've always been able to do. So that's all well and good, but I find that I wanted to make this more concrete. I think a lot of people are wondering, how specifically do the data engineers work with the data scientists and hand over their results one to the other in real life, in a real project? So to that end, I cooked up a small example. And so the rest of this webinar is going to be a quick walkthrough of the GitHub repository you see on the screen here. I'm going to put it in chat as well. And feel free at your leisure afterwards to browse this because it has all the code and it has a more detailed discussion of what's in it. But I'd like to walk through the high-level points of this example because I think it will make real how it is a data engineer could collaborate with a data scientist and a model deployer for a real use case. Now, we only have a tiny amount of time here, maybe 20 minutes, so I only can have time to explain a tiny toy use case. But I claim this is going to be a microcosm of how a real live project might work and how real data engineers might hand off and work with real data scientists. So the motivating example here is going to be an occupancy detection service. So the Acme Occupancy Detection Service is a predicting room occupancy from environmental sensors as a service platform, or Profess SaaS, I guess. So the idea here is they are going to predict whether a room has someone in it based on sensors in that room, maybe the humidity and the temperature and the level of CO2 in the room. It's a toy example, but I think it will be representative of actual use cases you can think of that maybe you're implementing in your business as well. So as Sean said, it's probably best to think of this problem as having three main parts: data engineering, data science, and model deployment. And we hear a lot about the data science, but I think we should talk about how all this comes together in one whole in the context of a real problem like this. But before I go further, let me ask a question. You should see a poll on your screen. And my question to you is, how is it that you transfer models to production? Maybe in your own application. So before we get into how you might do it with Spark and Data Science Workbench, I'm curious to know how you do it today. Do you serialize the model? How do you score the models as well? And by the way, choose more than one result if applicable. If you maybe serialize the model as PMML but score it with custom code, you could reflect that too. So lock in your answers now. Thank you very much. I see responses coming in. Very good. Thank you. In just a moment, I will reveal some results here. It looks like we've got a couple, almost 200 responses now. That's good. Let me go ahead and show some preliminary results. Yeah, not surprisingly, the answer is not applicable for a lot of people. And you know what? I think that the idea of deploying a model, maybe making it a REST API, a service that you can call interactively, it's a nice idea, but it's still not something a lot of organizations are doing. I think it does not surprise me as well that a lot of the solution today is scoring with some custom code or re-implementing the models the data scientists made in another tool or another place and re-implementing those to productionize it. So I think that the Hadoop ecosystem with tools like Data Science Workbench can help solve that part of the problem. At least we could possibly, in this world, have data engineers writing code in the same language with the same frameworks and on the same platform as the data scientists. So there isn't a need to literally throw code over the fence and have it re-implemented. Right, moving on. So in the context of this Acme occupancy detection problem, the data engineers are going to be responsible for ingesting the sensor data at scale. Now for our purposes, we're just going to work with a small CSV data set, but you can imagine this could be based on a large stream of sensor data arriving from rooms all over the place. Their job is to store it, secure it, clean it up, and transform it, and get it ready in some nice format for the data scientists to take over. The data scientists are going to take that data and do some exploration, build a predictive model. They're going to do this in the lab, kind of offline. They'll evaluate and tune the models, pick the right model, pick the right hyperparameters for the model, and publish that result. From there, someone else probably takes over. They take that model and they maybe run it at scale to get the final actual model parameters. They make sure it it works. It doesn't give wildly strange new results. Maybe it makes sure that it passes some compliance checks. Maybe they check it in and make sure it's versions. And then they're responsible for deploying that model to production, maybe running the live REST API services that are going to serve requests from that new model. These are all important roles, but they are actually distinct roles. Yet these should be roles that can collaborate on one common project and one common code base. For example, the data engineers. The data engineering component here should be pretty familiar to anyone out there who's a software engineer. Data engineering means dealing with data, writing code that transforms data. People doing data engineering are probably working in an IDE. They're checking code into a source control repo like Git. And they are probably writing tests and participating in a structured build, like with Apache Maven. All standard stuff for a software developer. So their job really is to take the raw data, and maybe in this case it's CSV data, it's sensor data, and write some code that creates a nice, clean, tabular representation of this data that the data scientists can work with. This is fundamentally what the data engineers are trying to do. Now I'm going to tab out and show you some codes and tools to give you a sense of what that actually looks like. One moment. Let's see. If I've been successful, you can see my desktop here. And this is the kind of thing, I'm going to open my IDE. This is the kind of thing that data engineers are going to do. They're going to work in an IDE. They're going to write Spark code, maybe in Scala, that reads data and transforms it, maybe fixes some problems with it. Here, for example, the CSV data actually has one more column than the header suggests, which is a bit of an error. So they might be responsible for cleaning that data, storing that data, and here producing a chunk of code that can read a Spark data frame. A data frame is a tabular representation of the data that's ready to be analyzed and ready to be modeled. So the software engineer, the data engineer, would check in this code to get, like in any other software project. This much is not surprising. I think this much is actually quite straightforward. And so that code would end up perhaps in a GitHub repository in Git. And if you've been following along, you'll probably already see this repository. And no surprise that it's part of a standard build structure, and it has a standard build file with Maven. that can compile and deploy the code. No surprises here. Now, normally the data engineers would actually hand over some code to the data scientists, and maybe they would build the artifacts and publish those software artifacts internally in a Maven repository. To keep this example simple, you'll find that actually the build just deploys the result as a compiled jar file in the project itself. So that actually makes it easy for the data scientists to take over and consume their output as code, run their code, get the data frame that the data engineers have produced, and then go to work in the data science workbench. So flipping back, let me see if I can, now I'm going to try to flip back to the presentation. Excuse me one moment. Let's see, so I hope we're back to the slides now. The data scientist is going to then take over and be responsible for turning this tabular data into a predictive model. So their job is the tuning of those models, maybe in some cases visualization as well, but we're not going to do visualization here. They are writing in some language, often Python or R, but here we're going to use Scala simply to match what the data engineers are doing and keep it simple. And maybe they're using libraries like SparkMLlib to do that modeling. Now, of course, they could be doing that in an IDE, but now we have things like the Data Science Workbench where those data scientists can work more interactively on cluster rather than pull data down or work offline. But I think in an ideal world, these data scientists are also using source control systems like Git. They are pulling data from, pulling code from, and pushing code to the same place that the data engineers are. So that at least all of this code, all of this product can be under one unified project in one place, and in that way pull together the efforts of both teams. So the role of the data scientist is going to be to take this tabular data, write some modeling code that's going to output some kind of model. And that's where their job ends. They choose the right model with the right parameters, and then the modeling team takes over. So I'm going to tab back out and give a little more detail about that. So here is the Data Science Workbench. I have already opened up a file with a bunch of modeling code that I've already written for this task. So on the left, on the console here, you'll see what the kind of code that the data science would be writing. For example, this code takes the method made available by the data engineers to load the data, they cache the data, they show the data, and then define a pipeline that transforms the raw data into a feature vector, and then runs a logistic regression on that data, and then establishes a parameter grid, a hyperparameter search, to go search for the best hyperparameters for that logistic regression model. So if I were to execute this code, and I've already executed it in the interest of time, you would see at the right the output. It outputs the code that's being run as well as the output from that code. And it crunches the numbers, it builds a bunch of logistic regression models, evaluates the accuracy of all of them. And in the end, it chooses a best model. And we can, for example, put out the parameters of that model. It looks like, for example, light and CO2 are positively correlated with someone being in the room, which is not surprising, for example. And we can even see the hyperparameters the model chose. 1.0 elastic net parameter means it chose L2 regularization and just a little bit of regularization, in fact. These are details of the logistic regression model. But it fit the training set quite well here, which is good. So the data scientist might be happy with this, and he or she, having written this code, having modified it and played with it for a while, and finding that it produces the model they want, could check this code back into Git. Now, I think this raises an interesting question. Data scientists are used to working in mostly a single file, not working in a big software project with folders and a large number of files. They're typically working on a relatively short section of modeling code. And that's what we've got here, but at the same time, we want this code to be part of a larger build. We want this code, this modeling code, to be built and tested and exposed to other groups as well. So actually, this project, this structure, pulls a little bit of a trick and wraps all this in a bit of boilerplate that makes all this code compilable in an IDE, in a Maven build. and actually makes all this code the data scientist has written a method that can be reused and called from maybe another group's work, like the modeling team's work. So with just a little bit of boilerplate, we're able to work as we're used to as a data scientist, yet produce code output that can be reused in a standard build by other teams that are not necessarily working in the data science workbench. So success, the data scientist has built a model that they're happy with, and what happens next here? Well, we want to go to production. And I'm going to flick ahead since we saw this. Right. We want to take this to production in some sense. And this is a big question mark for a lot of organizations. I've got a model, now what? What do I do with it? I want to apply it to data. Sometimes the answer is that that model is simply applied to a bunch of existing data offline in batch. And that's fairly easy to do, but often we want more than that. We want to make a real-time API out of this. A model is like a black box that takes inputs and produces predictions, and maybe we want to actually reuse that in our enterprise architecture. So the problem of deploying models is in turn, again, a bit more of a software engineering problem. So the problem is to take a modeling process, build a model, validate that the model is okay for deployment, that it works reasonably well, it's been tested, it passes maybe some internal policy checks. And so this may be, this is bordering on actual production deployment. So people involved in the deployment system probably do want to use automated tests, continuous integration systems like Travis. And they want to ultimately expose a REST API. And they want to build on standard frameworks that have been developed to publish models in standard formats like PMML as a REST API. So they're software engineers as well, but they're solving a slightly different problem. They're taking the output of the data science process, which is a model, maybe represented in a standard format like PMML, and turning it into a service that's going to stand up, that's going to scale, that's going to have uptime, that's going to be measured by its ability to respond to requests reliably. So I think this is one of the more interesting aspects. And again, before we get farther, I want to ask you one more time to answer a question for me. What is your requirement for model scoring? When you think of model scoring in your organization, is it something that needs to happen in real time? Do you need to respond to a request in maybe under 100 milliseconds with an answer from a model? Are your use cases more near real time, where if you can respond to new data and the output of a model in 10 seconds or so, that's fine? Are you happy largely with batch offline scoring of models every night or something? Or is it not applicable? So if you would, please take a moment, choose one, lock your answers in. There's no wrong answer. I'll wait a short time here for a couple more responses. We are close to 200 or so. And let's look at some results here. Kind of a mix. I think batch scoring dominates, and that's not surprising. In a lot of use cases, simply scoring the model offline is both simple and entirely sufficient. But increasingly, I think we do find in this age of IoT and sensors, and we do have this demand for doing things in real time. So in this example, we are going to see how to deploy a simple model as a service that could respond to a synchronous request via a REST API rapidly in a couple of milliseconds. So thank you very much. And I do understand that the answer there may be multiple answers for some of you, so I appreciate that. Right, so part 3, how do we get to model serving? I'm going to jump back to my desktop. Well, ultimately what we want to produce is a model. And the representation we're going to use is a standard XML-based format called PMML. So the model serving group's goal is to maintain this model and then deploy it. Really, so they have two jobs. They're gatekeepers to keep versions of models, and then they're responsible for deploying the models. So what's the model deployment engineer going to do? Well, they might also be writing some code, some Spark code. They may need to take that code that the data engineers have provided to read data, the pipeline that the data scientists have provided, and go run that at scale on the cluster to build the real deal final model on the full data set. And then save that and serialize that as, say, PMML. Here I've restricted myself to a very simple, short example that just runs the model as given from the data scientist and then serializes the result as PMML using a library called JPMML that can do that pretty automatically given a Spark model. So it's very simple, excuse me. And running it would probably be a matter of building the code. So this is what a deployment engineer might go, build the code. Actually, never mind that, that won't matter. Build the code and then run this modeling job on a cluster and have it actually produce a new model. Now I won't actually wait for this to finish, even though it'll only take a couple minutes because it doesn't actually matter that much. So what we will get in the end is a new model file, and like the one I showed you. And one of the key questions for the modeling group will be, is this okay to deploy? Is this new model we built, does it work? Does it seem like it passes some smoke tests? So that's why they might be writing some tests. They might actually have a known good set of test values they want to run against this model and make sure that the model is answering correctly in enough cases. So they might apply standard unit testing frameworks and unit testing approaches to read the model that's just been generated, run a unit test, and report its accuracy and ensure the accuracy is high enough. And this is where continuous integration systems can come into play to help us. As soon as a new model is committed, that could trigger a job on a continuous integration system like Travis that then would again build the code, make sure it all compiles, runs the model that's been checked in, and make sure that its accuracy is sufficiently high on some golden test set. So we can leverage automated build, automated testing to help us with the problem of model management and model verification. Of course, in the end, the goal is to produce a service. We have a PMML file. We should be able to deploy it as a REST API. And that is easy to do if you use frameworks like OpenScoring. OpenScoring is a project related to JPMML that provides a REST API container for PMML models. So I'm going to run this service. It's started. And then if I will publish my model using a simple HTTP request, here I'm just using curl to put the model to the server. And it accepts the model, and it will even confirm that it's received the model, and it tells you about the model. What are the fields? What are the inputs like? And then now this model is actually ready to serve. This is an HTTP server exposing a REST API that will answer questions based on the model. It's a little bit hard to show the REST API since it's just a REST API, but we can access that on the command line as well to give you a sense of it. So here, for example, we can post a JSON message containing a temperature, humidity reading, and so on, and see what the model says. The model comes back and says this is almost surely a 0, which means not occupied. So for these readings, the model says there's a 95% chance the model is not occupied. Simple example, just a simple service, but you can imagine a much more complicated model serving much more, doing more than just serving up a simple probability. But it can be just this easy. If you're able to build your model in Spark, export it as PMML in a standard format, then it probably can just be loaded up into a REST API like with OpenScoring. And voila, we have a production system. I'm going to return to the slides. So there are 3 distinct roles involved in getting a model all the way from raw data through to process data to a model to production. But all of these roles can collaborate with simple standard tools: Git, Maven, Scala, IDEs, the Data Science Workbench, Spark. And so stitching these roles together into a meaningful workflow is no longer a difficult and mysterious art. In fact, I think the simple example we have here, which again, you should take a look at if you're interested in reading more detail, the details of how this works. I think even this simple example is a realistic representation of how it could work for much more complicated projects as well. And this is good news for all of us. So feel free to have a look offline at this repository and read some of the write-up about how this works in more detail. Now, we're going to turn shortly to questions, but before we do that, small ad break. For those of you in the Bay Area, July 20th, we are running the 4th installment of our Wrangle Conference. It's a data science conference for data scientists by data scientists. It's a one-track event focused on problems like data ethics, how to build data science teams, and talking about recent trends in data science as well, how to build a data-driven organization, how does deep learning, for example, relate to the practice of data science. So if you're in the Bay Area, take a look at Wrangle. Thank you very much from me, Sean Owen, and also Sean Anderson. I think it's time to answer some questions.
Sure, Sean. Thanks for that overview, and pretty comprehensive in showing the parlay between the systems there. So I want to thank you for doing that all live with us here today. So we have some questions mounted up. Feel free to continue to submit them via the chat window. Want to just kind of cover a couple basic ones today. We have a user asking, is there a way to try the Data Science Workbench with the Quick Start VM? So today, the Data Science Workbench is not offered with the Quick Start VM. In fact, the service itself is a little bit larger than can be supported through the Quick Start VM. However, you do have the ability to download the Data Science Workbench, apply it to an applicable CDH cluster, and try it for a period of about 60 days. We encourage you to work with your account resources at Cloudera and identify, some of the best ways to get the best time during that evaluation period. Sean Owen and the extended team can also be resources in helping you evaluate that workflow. So that's one. Secondarily, people are asking how we would access the Data Science Workbench in Cloudera. So without getting into a lot of minutia about the architecture, if you're more interested in that, I definitely recommend that you view the first in this series of webinars where we do talk a little bit about the architecture. But this is essentially a web service. So the aspects of the product are deployed, it's integrated with CDH generally, and then the data scientist connects to the service via a web browser. So that is the general way that data scientists would connect to that. So that kind of covers the generic questions for this one, and we can start on kind of some of the other questions here. And Sean, maybe this is for you, and there's probably no right answer. We have one user asking, what's the best one, exploratory or operational, for freshers? And I'm not familiar with the term freshers, but I assume that means somebody who is just starting in their data journey. From what you've seen, what are kind of some of the common trends there?
Right, yeah. Being in the UK, I do recognize freshers. Thank you. I don't think either one is better in any sense. I think the exploratory role, as we've seen, is really the modeling piece of this. Taking data, building models, seeing what the data tells you, iterating again. So that's the classical data science role. The operational aspects are equally important. Those are the more software engineering oriented aspects. I came from the world of software engineering more than statistics and math, and others in the audience out there may be coming more from the statistics and math end. So I think either end's fine to start with. I think in the end you're going to want to have a little bit of both types of this knowledge in your arsenal, and certainly in your organization. But start with where you are.
Yeah, I think that's a good way to think about it. Just in our experience, I think there's no one right answer there. I think, sitting down with our users, we may have thoughts about how mature that customer is, but it's just generally based on what they're trying to accomplish as far as the business problem that's associated with those data science activities. So I think you actually covered this. Maybe we could take it a step further, Sean. One of the users has asked about does the Data Science Workbench support a seamless production model job running on Hadoop? And at the end, can it create an executable jar file? I know that you created a jar file in the first step in your example, but are there options for exporting the outcomes of the Workbench work as well?
Yeah, the output of the Workbench is really code. You're just editing files through the Workbench, really, and then the Workbench is helping you execute those files and iteratively explore data with the documentation and the code you've written in the Workbench. So I guess the answer is no, not directly. That's not the role of the Data Science Workbench. However, you could easily combine this with a proper software build and check your code into Git. It integrates with Git. And of course, do it that way. And maybe that's a better solution because we don't really need the Data Science Workbench to reinvent the idea of publishing and executing code. That said, there is one aspect of the Workbench that we didn't show off here that is relevant to your question. You can actually schedule files to run as if they're like a miniature job every night or every hour or whatever you like. So in a way, you can, treating a source file as a job, yes, you can actually use the Workbench as a lightweight scheduler to have that execute regularly.
Yeah, that's a great point. I think that was actually shown in Series 1 of this webinar. Stanley also asked additionally, what if the model does not have PMML yet?
Yes, so PMML has a pretty rich vocabulary to describe different types of models, but no vocabulary is going to describe every single type of model perfectly. And likewise, it's possible that some aspect of maybe Spark you're using doesn't have a corresponding description in PMML. So I chose a simple example here because as something that definitely would have a PMML representation. If not, you would probably then have to at least come up with your own serialization, which could be mostly PMML with some extensions to it. And then on the other end, write a little bit of custom code to understand your custom model. So it would just mean you have to choose a slightly different serialization. The rest of it wouldn't necessarily be changed. Got
it. Some more questions coming in, I think kind of based off of the demonstration that you ran. A kind of general question on how features are extracted from attributes. I imagine that there's probably a couple different methods to do that. Are there some that are specific to this example?
And this is a simplistic example where there's really no feature extraction. The features are simply taken from the raw data as is, and as it happens in this data set, it's all pretty clean, it's all pretty clear. There's no need to produce derived features. If you were going to do any of that, all that complexity would live with the data engineer, and they'd be writing that kind of code, that ETL, that aggregation code in their piece. And hopefully that could be to some degree insulated from the data scientists, or that's work the data engineers can do on behalf of the data scientists. I think this actually relates to another question I just saw a minute ago. Why were none of the examples negative examples? They are actually negative examples. They just weren't in the snippet I showed you. In the larger data set, there are. Yeah,
it's always nice when webinar attendees are paying attention to the examples in there. So
sharp eye, yeah.
We get a very, very sharp eye. So kind of related to that topic, Victor is asking how the Data Science Workbench can help with continual creation and deployment of models into production as aggregates grow.
Yeah, it's a related question, and it's one of my favorite ones. You're right. What we've shown here is a sort of a manual process, and I'm thinking of organizations where they need the process to have some manual checks and balances. Maybe it's a regulated industry. But in some contexts, you do want that model deployment, that model building and deployment to happen continuously. And we've got some other projects to show you along those lines. But what I would say here is imagine that the data scientist modeling code, that could also be taken and run and deployed on Spark Streaming in a way that causes it to rebuild the model on new data every night or every hour. So that's another thing the deployment group could have done with the output of the data science, the data science component. So for that, yeah, you would be looking at using things like Spark Streaming to continuously rebuild models, publish models, and if you like, you could fully automate the process you see here. As the data comes in, rebuild the model, check it into Git, go push the new model to your REST API. That's equally easy to engineer.
That's great. Yeah, and I think so we have a new question from Colin. He's saying, is the stack capable? And I'm assuming by this question we're talking about not just the Data Science Workbench, but the Cloudera platform in general. capable of things like monitoring model performance, triggering automatic recalibration, or alerting a data scientist if the model drifts too far off. And maybe that's outside the scope of these tools, but maybe we can talk about partners or other solutions that can bolt on.
I think the answer is yeah, but you would have to build it. For example, you can imagine writing a script in Data Science Workbench that builds a model, evaluates it on a validation set, and then raises an alert or fails itself if the evaluation is not high enough. And yeah, within the lightweight scheduler in the Workbench, you could cause that failure to trigger another job or an email or something. Outside of that, I should also mention we have a separate labs project called Oryx, which is actually is a reference architecture for building models continuously, updating them and serving them, built on some of the same concepts here as well. And yes, for example, that framework does have some answers for automatically validating and tuning models and actually rejecting them and raising alerts if the model doesn't validate. So there's plenty of ways to do it. You probably would have to build that into your application logic, but it's straightforward.
And Sean, what's the best resource for people to understand a little bit more about Oryx? I know we have a section of our community forum that's dedicated to that, but if our users are interested.
It's on GitHub. It's simply an open source project, and I will paste the URL of the project in the chat right now.
Great, thanks. One final question for you, Sean. What is the best way to create pipelines in Spark and Scala? I imagine there's maybe a couple answers to that question, but in your practice.
Sure. I mean, a lot of modeling jobs aren't really just one stage. They're really a whole pipeline of operations, preparing data, preparing features, maybe chaining together models. And fortunately, Spark and the Spark MLlib project has a notion of ML pipelines. They're literally called pipelines. And that's actually, I think you saw a little bit of that in the example here, where we chain together a component to assemble the feature vector and then build the model. So Spark has an abstraction for this, and it works well. And so you should use that. And the upside is that the library I use to generate PMML also understands Spark pipelines and can, in most cases, translate that correctly to the appropriate PMML representation.
Yeah, I think that's key to kind of piecing together, all of these operations that are involved with the data science workflow. So that's definitely helpful, and I would encourage viewers of this webinar to continue to stay tuned in to our engineering blog and our community resources as we start to give better kind of best practices of doing that in the coming months. A couple rapid-fire questions aimed at the Data Science Workbench specifically. I'll take an attempt at kind of answering them. Dustin writes, how do you deal with models being developed with other tools like H2O, for example? Platforms like H2O, RapidMiner, Nime, DataRobot, many of those are Cloudera partners and are certified to run on CDH. And just to kind of level set, specifically, we as a platform provider have no specific affinity to how our customers require to develop their data science models, to deploy them, to tune them, to do all of that. And so our general stance is that if H2O or DataRobot or any of these visual tools or otherwise are the right tool for your data scientists, we encourage them to use them natively on the data science platform. I think of it in the same vein as I thought of BI tools, right? We create a common platform that allows a Tableau and a MicroStrategy and a Qlik user to all work on top of a common data platform. While the Data Science Workbench is a handy interface for a Python and R developer, we definitely do not want to limit consumption of Hadoop data and work on the Hadoop platform to just those protocols. And so we believe the right tool for the right practitioner in ensuring that we can leverage our partner ecosystem. Now there's a couple levels of integration there. There's somebody using H2O directly on our Hadoop data and leveraging access engines like Apache Spark. And then for specific providers of platforms that produce their own algorithms like H2O, DataRobot, those can actually be used natively inside the data science workbench. So you can import in algorithms from H2O or from MLlib or otherwise, and integrate them directly into the data science workbench. Another question is, how powerful is the data science workbench compared to any regular IDE? Rather than give my opinion, as I'm slightly motivated to tout the accolades of the specific tool, we encourage you to try it for yourself. The data science workbench is built off of a kernel of a very popular data science collaboration technology. And so at the end of the day, we believe that it supports a majority of the operations that somebody that needs to share code, that needs to do interactive visualization, that needs to produce data frames. We believe that it has a majority of the components that our customers, specifically those in the Global 8000, demand. So I would turn that question back on you guys and ask us for an opportunity to be part of that evaluation in comparison to what you use today. And then a final question is around what type of parameters do we need to evaluate hardware sizing of the data science workbench? This would be a fairly lengthy question to answer pre 1 week ago. However, the product is generally available. We've released all of the installation instructions as well as an architecture guide and hardware sizing requirements. All of those are readily accessible via our downloads page, so I encourage you to go to that link and check out check out the downloads page and all of the related documentation. So with that, I'd like to conclude our data science topic for today. This is the final in our 3-part series of data science webinars. I would say that don't expect for topics around data science, models into production, deep learning, machine learning to go away by any means in the near future. And the data science workbench and other components that contribute to this dialogue are quickly driving a lot of helpful content from the Cloudera side. So continue to keep a pulse on what we're doing here, and we'll do our best to reach out to you guys once we have some similar topics to talk about either in this series or in a following series. So with that, Sean, any final words for our attendees on the line?
No, thank you very much for joining. Thank you for your time. And maybe I can stick on chat for a minute to answer a few quick questions we didn't get time to answer. Otherwise, thank you very much.
That's great. So it looks like Sean will fire off some answers directly to the askers and this one, and we will conclude today's webinar presentation. Again, thank you all for joining, and stick with us for more topics around data science in the enterprise. Thank you very much.